Welcome back to another Explainer. Today we're diving into a massive paradigm shift happening over at the Pacific Northwest National Laboratory, PNNL for short, and alongside their brilliant partners. We are talking about the dawn of future autonomous science systems. And listen, this isn't just about throwing faster computers at a problem. It's about fundamentally changing the whole shebang, how we conduct research, how we discover new materials, and how we actually secure our borders, all without human limitations getting in the way.
Okay, let's dive into this. How do you measure everything, everywhere, all the time? Well, it's a trick question, right? Because you just can't. Right now, human-driven science and global security are frankly drowning in data fatigue and labor bottlenecks. I mean, think about it. Whether it's a researcher painstakingly mixing chemicals by hand or a security operator staring blankly at endless, continuous raw video feeds, the human element is literally slowing down the sheer volume of discovery and awareness that we desperately need. We simply have finite resources trying to process an infinite amount of data.
So here is our roadmap for today. We'll be exploring this self-driving science arc across two very different arenas: robotic microbiology labs and rugged field sensors. First, the autonomous science revolution. 2. Self-driving biology with AMP2. 3. URSA for accelerating materials discovery. 4. Orchestrating sensors with persistent dynamics. 5. Smarter intelligence at the edge. And finally, maximizing our finite resources.
All right, kicking things off with Section 1, the autonomous science revolution, moving past human bottlenecks.
And this brilliantly illustrates the core problem we're facing. Imagine highly trained scientists stuck doing manual pipetting day in and day out, or security personnel exhausted from monitoring continuous, totally empty video streams. On the human-driven side, it's incredibly labor-intensive. It demands manual coding, continuous streaming of heavy data. It's just exhausting. But the autonomous paradigm, that flips the script. It leverages AI agents that make active decisions, executes physical tasks through actual robotics, and processes data right at the edge. It's a massive shift from outdated brute force to truly elegant efficiency.
Moving on to Section 2, Self-Driving Biology with AMP2, Automating the Microbial Lab.
So AMP2 stands for the Anaerobic Microbial Phenotyping Platform. Developed by PNNL and Ginkgo Bioworks, it is essentially a massive, quote-unquote, self-driving robotic biology lab. Its main job is to systematically measure exactly how microbes behave without oxygen across a really broad range of conditions. To make this happen, the system uses these sealed chambers that are all connected by robotic tracks totally run by integrated, automated software. And the best part, this completely frees scientists from that soul-crushing, time-consuming physical labor. Plus, AM2 is really just the precursor to M2PC, which is an even larger planned AI-enabled self-driving lab over at PNNL. By taking human hands out of this repetitive work, we are rapidly accelerating breakthroughs in sustainable manufacturing and energy security. It's a real game changer.
Let's move to and see how this builds into Section 3, URSA, Accelerating Materials Discovery, where AI agents are actually building fusion alloys.
URSA is this fascinating agentic system that's part of a broader project called Artemis, developed in collaboration with Los Alamos National Laboratory. Now, when you hear AI foundation model, you probably instantly think of a language model, right? But as one of the project leads jokingly noted, they aren't trying to write mathematical proofs in the style of the Grateful Dead. URSA is an AI that acts as a surrogate for complex modeling. It actually predicts and discovers new materials, like entirely new alloys that can withstand the crazy extreme temperatures and radiation at the core of a fusion reactor. But here is the really cool part. It doesn't just predict, it acts. The AI designs a recipe, and then automated dispensers and robotic arc melters physically meld those pure elements together to test the physical materials. This autonomous feedback loop pushes computational design directly into the real world, meaning highly trained scientists no longer have to spend their precious time writing basic Python or Bash scripts. The system handles the entire execution.
All right, Section 4, Orchestrating Sensors with Persistent Dynamics, Stepping Out of the Lab.
Now, what's really interesting about this slide is seeing this tech out in the real world. Meet the Edge Processing Monitoring Unit, or EMU for short. It's a weather-resistant, rugged, multimodal hardware platform. It is literally designed to sit out in harsh environments and execute dynamic tracking without a human operator having to babysit it.
The whole philosophy behind this system is summed up perfectly by Los Alamos scientist Norma Pauly. She says, modern monitoring systems face a fundamental constraint. It is neither practical nor affordable to observe everything everywhere all the time. And she hit the nail on the head. True intelligence isn't about hoarding all the data. It's about measuring the right thing in the right place at exactly the right time.
So how does that orchestration loop actually work autonomously? Let's walk through it. Step 1, an edge sensor detects an anomaly. Step 2, the system's coordination engine autonomously evaluates this and generates a tasking request. Step 3, it dynamically tasks other nearby multimodal sensors to form a temporary, collaborative working group to track the event. Step 4, once the event is verified and characterized, it escalates an alert. P&L experts like Lee Burke and Jeremy Hawk utilize their backgrounds in open-source agent frameworks to make this brilliant, decentralized, multi-agent communication logic possible.
Which brings us to Section 5, Smarter Intelligence at the Edge, Filtering the Noise.
Yes, you are seeing that correctly. This is the literal emu bird logo for the Edge Processing Monitoring Unit project. But humor aside, the computing happening on these emus is serious business. You see, instead of sending continuous, heavy video streams back to a central hub, which eats up massive, finite bandwidth, the units process the raw data right there on the device. They compress it into tiny, high-value metadata alerts, only sending a message when something actually matters.
And just look at how diverse these commercial off-the-shelf sensors are, all powered by embedded NVIDIA Jetson modules. For instance, optical nodes use visible and near-infrared cameras specifically tuned for tracking heavy transport trucks. Vibrational nodes, they use direct contact accelerometers to track the speed transitions of mechanical fans in industrial cooling towers. And to round it all out, acoustic nodes utilize microbarometers to detect low-frequency pressure waves.
So the crucial point is that this system dynamically adapts in real time. Because it processes at the edge, it's specifically tuned to filter out irrelevant noise. Like if a wasp lands on a security camera lens, the system knows to ignore it rather than triggering some massive false alarm. And it's highly resistant to evasion. If a suspicious truck is being tracked visually and it drives behind a building, the system seamlessly tasks the acoustic sensors to take over and maintain that situational awareness.
Finally, Section 6, maximizing our finite resources, real-world applications. By eliminating those pesky false positives and dynamically orchestrating resources only when they're actually needed, we save incredible amounts of human labor, bandwidth, and financial cost. This award-winning architecture is actively being applied to high-stakes missions like nuclear non-proliferation monitoring, but it's also highly transferable to massive commercial uses, like tracking wildfires, coordinating emergency responses, and securing large distributed infrastructure like gas pipelines.
From microscopic anaerobic chambers to rugged edge sensors out in the wild, the era of self-driving science is absolutely here. PNNL, LANL, and their partners are finally giving scientists and security operators their time back. So we leave you with this final thought. As our science and our security monitoring become fully autonomous, what new human frontiers will we finally have the time to explore? Thanks for joining us for this explainer, and we will catch you next time.